So today topic is back bonding in metal complexes. And this can be back bonding can be explained by IR spectroscopy. So that also I will explain here. So we know that metal, so in a metal complex, so metal is the electron, like we can say it is a acidic, and this will be a basic. So there is a transfer of electron density from the ligand to metal. So this is the concept. This one we will expect in a metal complexes. So when we have a metal which is binds with water molecule and ammonia and CO. So compared to CO, water and NaCl are strong Lewis acids. Lewis bases. So CO is Lewis acid. Okay. So why we are observing the back bonding in the metal complexes? So in these two cases we will not expect any back bonding, but here only we are expecting a back bonding. So this is because, so when we have a metal, it attaches with the Lewis base. Like we can take water molecule. So this is the filled orbital of metal, and now this electron density goes from here to here. Okay, so there is no vacant orbital on the oxygen. Similarly with ammonia also. And when we have a CO, here we have CO, and CO is having a vacant orbital, and this is the filled orbital and this unfilled orbital. The electron density transfer takes place from the ligand to metal, and the whatever electron means here empty orbital is there on carbon. Now the electron density from the metal filled orbital, that means this orbital, will takes place into this one. Okay, and if you see here, we are expecting only one bond here, that is ligand to metal, but here we are expecting two bonds. This is the one, this is from the, like this is because of the electron density transfer from the ligand to metal, and one more bond also forms. That is forming because the electron density of the filled orbital of metal is transferring into the empty orbital of the ligand. So here we will get a double bond. So this bond is called as back bonding. This bond is forming by the back bonding, and in this case carbon is having a valence of 5. That is not acceptable, so that's why this triple bond will convert into double bond. Okay, so this is the actually the back bonding. So why CO is pi acceptor, why not water and ammonia? If you see the orbital diagram for CO, we have this will be pi orbital, this is sigma, this is pi star orbital, and this is the sigma star orbital. So in case of CO, we have total of 6 electrons. So those 6 electrons will fill like this: 1 2 3 4 5 6. So this pi star orbital is vacant here. So because of that reason, the CO is acting as a pi acceptor. So there is a possible question that which orbital is involving in the back bonding in case of CO. So the answer will be the pi star orbital. Now because of this back bonding, so what will happens to this stretching frequency of CO? We know that the stretching frequency of CO is directly proportional to the bond order. Okay, we can also say that bond strength and inversely proportional to bond length. So this we know that. So now because of back bonding, the bond order of CO is changing from the 3 to 2. So because of that reason, the stretching frequency of CO will decreases. So when we have a C triple bond O, if we record the IR spectra for C triple bond O, so we'll get a frequency around 2143 centimeter inverse. And when it's attaches to the metal, the stretching frequency of CO will decreases. That will be 1852 2143, and means close to 2143, not exactly, close to 2143. And when we have a bridged CO, in that case we'll get a frequency around 1700 to 1850. And when we have a carbonyl is attached with 3 metals, in that case we have a 1600 to 1700 centimeter inverse. So here we need to remember these ranges. It's very easy to remember. For CO, just remember 143, then just keep 2, so 2143. And for this remaining 4, it's very easy to remember. Just remember 8050, so that will reflect here, and now 1700 will reflect here. Just we need to remember these values, 1600, 1850, then it will be very easy. So it's very simple. So when we have two metals, in that case the extent of back bonding will be more. So because of that reason, the CO stretching frequency further decreases. And when 3 metals are there, even more, means like the back bonding will be more, in this maximum in this case. Because of that reason, we will get a less frequency when metal is attaches to the CO is attaches with the 3 metal atoms. So this is about CO, and there are some factors which affects the CO stretching frequency that we will see now. The first one is the electron density on the metal. On metal. So when metal is attached with the electron donating groups, in that case what will happens, there is a electron density transferring takes place from the electron donating group to metal. In that case, metal is becoming a electron rich. When metal becomes electron rich, it has to reduce the electron density on it. So because of that reason, whatever the vacant orbital is there on the CO, the electron density will be transferred from here to here. And now the bond order of CO will decreases. This will be double bond MC, and this is also double bond. This is when we have an electron donating group. When metal attaches with the electron withdrawing group, in that case the electron withdrawing group withdraws the electron density, right? So the electron withdrawing group will take electron density from the metal, and now metal is electron deficient in nature. So the chances of CO back bonding will be very less. In these cases, the stretching frequency of CO will be more. Okay, so we'll take a few examples. We have a phosphorus ligands. We have to remember two orders for phosphorus ligands. Sigma donor capacity. So sigma donor capacity will be maximum for PCY3, then PE3, then trimethyl phosphane, then PPH3, POCH3, POPH3, PCl3, and then PF3. And next we have a pi acceptor capacity, and this is just reverse of the sigma donor capacity, PF3 will come first, then PCl3, then POPPH3, POCH3, PPH3, PMA3, P3 and PCY3. So here it's very easy to remember. It's not like this order can be, we can say that this will be strong pi acceptor and these are not pi acceptors. Okay, like that we can remember, and it's very easy to remember. Just take the concept of electronegativity. So here fluorine and chlorine is more electronegative, so on that basis PF3 comes first, then PCl3 will come first. So then it's clear, two are clear. Then we have a oxygen. So anyway, oxygen will be more electronegative than these carbon having carbon. So because of that reason, oxygen has to come next, and that too we have a competition between the phenyl group and methyl group. We know that phenyl, we have a more sp2 character here, and here we have a sp3 character. We know that sp2 character will be more acidic compared to sp3. So on that basis we can give this order. POPH3 is higher than the POCH3, and here also same, we have a competition between the PPH3 and PME3. Here also we can use same concept, and then we have a P3 and PCY3. So this is the order. It's very simple to remember. Just take the concept of electronegativity, and imagine that we have two complexes where metal is attached to the PF3 and CO. This is the complex A, and complex B, we have a metal attached to the PCY3, and complex C, we have a metal attaches to the PPH3. And here if they ask metal to carbon, similarly carbonyl stretching frequency as well as the CO stretching frequency. So we know that, as we can see here, when electron donating group is there, the electron density on the metal is increasing. So because of that, this is involving in the back bonding. So when it's involving the back bonding, there is a formation of a double bond between the carbon and metal. Okay, so because of that reason, the bond order of CO is decreasing, right? So here we have PCY3 and PPH3. In these two cases, the metal is electron rich. So here the metal is electron deficient. In that case, the CO stretching frequency will remain as such. Okay, for CO stretching frequency, A will be more. Then, so the extent of back bonding is higher in case of B, right? Because of PCY3 is more electron donating group. So because of that reason, this will be having a least CO stretching frequency, and this will be in between. So this will be C, and this will be a B. So this is for the CO stretching frequency. And what about the MC? So just remember, because of back bonding, CO stretching frequency will decreases and MC stretching frequency will increases. So where more back bonding is there, that will be having a more possibility for M double bond C. So here the more back bonding is present in case of B. So B will be having more metal carbon stretching frequency than C, and at last A. So this is the how the groups on the metal will affect the stretching frequency of CO. And next we have like metal complexes which are having the charge. Just A, we have just imagine we have three complexes. So nickel CO4, then cobalt CO4 minus, and Fe CO4 2 minus. So here we need to see like, okay, before solving this one, we need to solve one more question. Like we have three complexes. Imagine like Cr CO6, second is Mn CO6 plus, third is Fe CO6. minus. Imagine we have these three complexes. I think this is not possible to exist. We take C complex will be CO4 minus. So these are the three complexes we have. Here we can say the Stretchy frequency of CO based on the charge also. Okay, so we have A plus and A minus. So which one will be having more electrons? A minus will be having more electrons. That means A minus is electron rich. So with that concept we can solve this question. So here we have a negative charge. That means this cobalt is a electron rich, and here we have a positive charge on manganese. That means manganese is electron deficient, and there is no charge on the chromium, so this is a neutral. This will be in between. So since this is the more electron rich, so the extent of back bonding will be higher in this case. So if extent of back bonding is more, the CO Stretchy frequency will be less, nu CO, so C will be less. And next we have a chromium and manganese. So manganese is electron deficient because of the positive charge, and there is no charge on the manganese is a electron deficient because of positive charge, and there is no charge on the chromium because of that. This is a little bit electron rich compared to manganese, so the manganese will be highest because of electron deficient. The extent of back bonding will be less in this case, and it will be in between. So this is the order. And if the question is like about the metal to carbon, then this will be reverse, where the extent of where is the extent of back bonding is more, that will be having a more stretching frequency of MC. So C will come first, then A, then B, and we will come here now. So here we have a positive charge, negative charge, and neutral, but here we have only neutral and negative charge. So where more negative charge is there, that is more electron rich, so their extent of back bonding will be more. So here we have a more negative charge, because of that the iron having a more electron density on it, so because of that reason extent of back bonding will be more here. So automatically nu CO Stretchy frequency will decreases. This will be C less than B and less than A. So NiCO4 is having a more stretching frequency compared to cobalt CO4 minus and FeCO4 minus. And then we have a complex CO2 CO8. So IR is one of the best technique to identify this complex. I mean, there is it exists in the two form, solution form as well as solid form. In the solution form, all carbonyls are terminal, whereas in case of solid in solid state, it exists with the two carbonyl groups that are bridged, and remaining 6 are terminals. This is in the solution state and this is in the solid state. If we record the IR spectroscopy for the solution state, we'll get selectively only terminal carbonyl stretching frequency, whereas in case of for solid, here we'll get a stretching frequency of terminal as well as a bridge. We'll get two stretching frequency in this case, CO to CO8. So when we have two complexes, vanadium hexacarbonyl and vanadium hexacarbonyl anion, so if they ask question which is having a more the VC bond length, which is having more VC bond length, means vanadium to carbon bond length. So we know that bond order is inversely proportional to bond length, directly proportional to bond strength, right? So this is about the VC. That means like where extent of back bonding is more, that will be having this bond order of 2. Okay, so here extent of back bonding is more because vanadium having a negative charge. Negative charge means is electron rich. because of this negative charge, this will be having a more electron density, and there is a possible for the back bonding. In that case, the bond order of vanadium and carbon will be 2. So here it will be having a less bond length. Bond length of VCO6 is greater than bond length of VCO6, a negative charge. And then the IR stretching frequency of complexes Fe, CO5, Fe, CO4, PF3, Fe, CO4, PCl3, Fe, CO4, PME3. So we have 4 complexes here. So we need to identify the new CO stretching frequency, which order. So we know that if electron withdrawing group is present, so there is a chances for the less back bonding, so they will be having a more CO stretching frequency. So if you see this one, these two are the electron withdrawing groups. So second complex will be having more stretchy frequency, then third complex, and now here we have a electron donating group, and this is a neutral. So if electron donating group is there, that means that will be giving us some electron density to the iron, so that is making a this complex more electron rich. Because of that, extent of back bonding will be more in this case, though that will comes at last, and neutral one comes here. And if they ask iron to carbon stretching frequency, then it will be reverse: 4, 1, 2, 3, and 2. This is the order. And we have 2 more complexes, rhenium oxygen 16 I, and 2 moles of acetylene. This is the complex 1, and complex 2 is rhenium oxygen 18 I, CH triple bond CH twice. So here we need to identify which one is having a more stretchy frequency of C triple bond C. So here we can't identify it by the back bonding. Here we just use the concept of reduced mass. We know that reduced mass is inversely proportional to the force constant as well as stretchy frequency, right? So where we have a more reduced mass, that will be having a lesser stretching frequency. So here we have a more reduced mass of oxygen 18 is more compared to oxygen 16. So because of that reason, the stretchy frequency of 1 is greater than stretchy frequency of 2. And one more question I like to discuss. We have a H3B, CO, and manganese, CO6 plus. Third complex will be Cr, CO6, and fourth complex will be V, CO6, a negative charge. So now we need to identify which one is having a more metal to carbon bond length. So as I said that if there is a back bonding is there, in that cases the metal to carbon bond order will be more. So bond order is inversely proportional to bond length. Which is having more bond order, that will be having a less bond length. So in that case, here we have a vanadium CO6 minus. This is electron rich in nature. So because of that, the extent of back bonding will be more in this case. So that metal and carbon exist with a double bond. So the bond length of this complex, metal to carbon bond length will be very less because of the bond order equals to 2. So this will be the first. I'm just giving order. 4 is less than. And next we have a neutral and positive. So positive means electron deficient, so there is no chance for the back bonding. I mean, chance will be there but very less. And compared to positive, the neutral complexes will be having a more possibility for back bonding. So then 3 will come and 2 will come next. And what about this one? So we know that BH3 is the Lewis acid, and these will act as electron withdrawing groups. Okay, so these will act as a electron withdrawing groups. So the extent of back bonding in this case completely ruled out. So because of that reason, this comes at last. So this acts as electron withdrawing group. So when it's acting as electron withdrawing group, in that case the back bonding will be less, so the order will be like this. So this is about the back bonding and IR spectroscopy. I hope everything is clear. If you have any doubts in this recording this, you can comment in the comment box. Thank you.